Hi, I'm Yoyu. Thank you for joining this session. I'm a cloud data architect from Cloudreach. Today I'm going to present one of my personal projects, People Atlas, and how I use AWS for natural language processing. I don't know how virtual meetups are for you. I certainly find presenting virtually is more challenging. That's why I employed this rubber duck technique. I have three rubber ducks right in front of me to pretend they are my audience. Thank you, rubber ducks. To start with, I want to present the project a little bit so you have a better understanding of what this use case is about. Let me switch to the second screen. Now let's go to the website of People Atlas. So the idea of the project is for the users to explore how the world is connected through people. For example, here we can see the path of Ada Lovelace, where she has been or where her influence has reached. You can search for pretty much anyone who has a Wikipedia page. Let's search for someone that we know definitely is included by the website. For example, here we search for Charles Darwin, and we can see where he was born, where he has been, where he studied, and so on. And not surprisingly, we got this data from the person's Wikipedia page. I used a mixture of traditional web scraping and natural language processing to extract key information, such as the place, the name of the place and the date from the Wikipedia text. Currently, there are about 10,000 people included by the website. But you can also search for someone that is not included in this website yet. For example, let's try the name George Floyd. Yeah, so here it says, you are the first person who searched for this name. Why don't you come back in a few minutes to see if we found them? Why can't we return the result immediately or just let the users to wait? I'll come back to this question a little bit later. What happens here is it triggers a ECS job as a background. Here we can see there is an ECS task already running that extracting the information for us. We will come back in a couple of minutes, and before that, let's go back to the architecture of the project. As you can see here, the architecture of the project is fairly conventional. I believe many of you are already quite familiar with the majority of the services here. For example, we have Amazon S3 for static website hosting. We have Amazon Cognito for identity management. We have AWS Lambda for serverless backend. And we also use AWS S3 for data storage. For example, when we search for Charles Darwin, because his data has already been extracted before, Lambda can directly go to S3 and retrieve this information and return to the user. But when we search for George Floyd, because his data was not there yet, the Lambda kicks off a container job which goes to the Wikipedia page and extracts the information. So NLP here stands for natural language processing. When we talk about natural language processing, many of us will assume this is something for the data scientists to do, or this is something super advanced, or this is something necessary involves machine learning. I thought so too, but I found this is not the case. People Atlas, to be fair, was the first project I used the NLP myself, apart from using something like Alexa. I actually found it's not so difficult to get started. What I used was the Python Natural Language Toolkit, NLTK, which is also one of the most popular natural language toolkits at the moment. If you want to learn more about this library, you can go to nltk.org/book. This is a very guidebook of very good guidebook of natural language processing in general, as well as this toolkit itself. Next, I want to talk about a few basic concepts or techniques of natural language processing and how I use it in my project. The first concept is tokenization. Tokenization simply means to break down a sentence or a piece of text into a list of individual words. For example, here we have the sentence, in 1845, its family moved to Le Havre in Normandy. After tokenization, it became a list of which the first word is in and the second word is 1845 and so on. So tokenization is actually the foundation of many natural language processing jobs. For example, after tokenization, we can count the frequency of each word in a piece of article. Therefore, we can determine the theme of this article. And similarly, we can, in search engines, we can also reverse match keywords to different articles and find the ones that are most closely related to our search keywords. So this is tokenization. The second technique I used is called word stemming. It simply means to find the stem of each word. So in English language, instead of saying move, we may say we moved or he moves. But no matter it's moves or moves, in both cases we mean move. So word stemming can help us to remove this kind of disturbancy caused by the different forms of words. So, for example, in my project, I need to identify some signal words that indicates a movement. For example, things like born, move. So that's why I apply word stemming to already tokenize the word list of each sentence, and then I look for the keywords move or born, and then I decide whether to further process those sentences or not. So the next technique is called part of speech tagging or pause tagging. So again, pause tagging is applied to already tokenized words. So for example, for the sentence we had before, after pause tagging, what we get is, for the word in, we applied a tag in, which means preposition. And for the word 1845, we applied the tag CD, which means cardinal digit. And for the word his, we applied the tag $, which means possessive pronoun. So by apply tagging, it helps the machine to understand the structure of the sentence. So therefore, it's one step towards natural language understanding. And we don't stop there. We normally want to do something further to the already tagged sentences, which is a technique called chunking. Chunking means to apply a grammar to the sentences to help us further understand the structure of each individual sentences. For example, here we have a problem that we want to extract the years from those sentences. But as you can see, in the first sentence, 1845 is obviously a year. But for the second one and third one, 165 and the 35 here, they are not years. Although they are both numbers, but they are not the kind of numbers we want. And that's why we can define a grammar. This grammar essentially means I want to find a combination which starts with a preposition followed by cardinal digits, and then I exclude the preposition, so I only get the cardinal digits left, which is the year we are looking for. So this works very well for the first and the second sentence. So for the first sentence, before 1845, we have a preposition here, and then followed by the cardinal digits, 1845. So we know 1845 is the year we are looking for. And in the second sentence, the number 165 does not have a preposition in front of it, so we know this is probably not the year we're looking for. But in the third sentence, there's a little bit problem. While this grammar works well for 1874, but for the digit 35, it also has a preposition in front of it. So if we just apply this grammar, our program will think 35 is also the year, which is not true. So this is where the natural language understanding can get complicated. You can go infinitely in depth into achieving a better understanding of text, but in my personal opinion, we have to stop at somewhere. In my case, I found I stop here is actually good enough, because when I analyze an article, you don't have just the one sentence. You extract years from many different sentences. If you have a number which is identified as a year, but is obviously not in the normal range of other years, I can say, okay, this is an outlier, therefore I just ignore this number. So it works pretty much, it works very well for me. But of course, if you want to do something really sophisticated, you can either go more into depth in your program, or you can use something that is already tuned much better than by the other data scientists. Use something like Alexa or Google's Dialogflow to achieve the same result. But in my case, I found this simple technique is already enough. So those are the 4 basic techniques. Next, I want to talk a little bit about this ECS component. At the beginning, I did want to use AWS Lambda for the NLP data extractor as well, but soon I discovered there were some limitations of incorporating NLP in a Lambda function. First of all, for Lambda functions, there is a deployment package size limit, which is 250 megabytes, including all the layers. Once I thought I would never go over this limit, but it's not the case for NLTK. Because when you use NLTK, the chance is you also need to use some of the libraries, and those libraries are relatively big. Also, when you do some sort of data analysis, you may come across non-pure Python modules, such as NumPy. Those modules, they need to be compiled for Lambda environment specifically before deploying. And after that, they can take quite a lot of space as well. So in my use case, I couldn't reduce the size of my deployment package to under 250 megabytes. So that's the main reason I used ECS instead of Lambda. There could be other limitations as well. For example, as many of you probably know, for Lambda function, the running time cannot exceed 15 minutes. So if you have a lot of text to be processed, I can totally see that this can be a problem. And also there are other dependency issues. We already talked about non-pure Python modules, and depends on your use case. You may also need to use some OS dependencies, for example, a library that is installed at Linux level instead of as a Python package. In that case, you certainly need to use something like a container instead of function as a service. I used ECS Fargate as the container runner. ECS has 2 flavors. One is you can run your containers on EC2 clusters. Another is you can run your containers on Fargate clusters. Fargate is essentially a virtual cluster where the compute instances are transparent to you. So all you need to do is just to configure it and run the containers. You can also use Kubernetes with Fargate. The reason I use ECS is for the simplicity, because I can do everything just within CloudFormation or serverless framework without need to touch kube control or having separate Kubernetes configuration files. As we have seen before, this is the interface of ECS. If we go to clusters, we can see a cluster that has already been created. As we are not using the EC2 cluster type, we will not see any container instances here. ECS actually supports two different types of containers. The ones we were using is called tasks. So tasks are triggered only when needed. So in our case, only when someone searches for a person that is not previously included by the website. They are triggered and they only run once. Another type of container is called services. Services are non-running containers that are normally exposed as a service, such as a website or web backend service. Now, I want to go back to the website and see if it has found George Floyd. Here we can see it did find the information from the Wikipedia page and also mapped the key events on the website. Now we can go back to our first question: why we can't, when a user search for a person that is not included by the website, why can't we let the user wait for a result to come back? So this has something to do with how ECS is designed at the moment. While, as we introduced before, ECS supports service container type, but to expose something as a web service, you need to have a long-running container, which goes against the purpose of being serverless. The purpose of being serverless is we don't want to maintain any compute resource when we don't need them. But obviously this is not ideal. We can't use the task container type either, because the issue is the starting time of task containers are relatively long at the moment. By relatively long, I mean 1 or 2 minutes. As we know, for a web service, even 5 or 10 seconds waiting time is too long for the users, so let alone 1 or 2 minutes. So I really do hope AWS can have a product that offers a similar experience as Cloud Run in Google Cloud. Cloud Run is very similar to AWS Fargate. The only difference is the starting time. With Cloud Run, you can use containers as your serverless web backend. When the service is not requested by the users, you can set the number of containers to 0. When the users request the service, however, Cloud Run can spin up the containers almost instantaneously. I quite like this experience as I used Cloud Run in previous projects before. With this constructive feedback, I would like to wrap up this presentation. Here I also included some useful links in case you want to drill down into some specific topics covered by today's presentation. And thank you.
Hello, Yoyu. Can you hear me?
Hi. Yeah, I can.
Great. Thanks for the presentation. Before we go to questions from the audience, which I'm hoping there might be some, but I can't see any. This is obviously a sort of hobby project for you. What's the next iteration? What are you going to do next with it?
Well, it's a very good question. So initially, I created this project because I'm a big fan of art and art installation. So initially, I had this idea of making actual physical installation. They're ones you can see in kind of the art gallery or museums or public spaces. So I had this idea of creating this project about 2-3 years ago. And initially I wanted to make it a physical installation that can be displayed at public places to raise awareness of that. Essentially, like immigration could be, well, I guess it goes both ways, but can be something positive for the society as well.
Cool. So presentation in public is what you're aiming at with it, ultimately.
Yeah, something like, for example, using some sort of VR or AR. I had this prototype where you can use kind of motion control to rotate a virtual globe. Yeah, so the viewers can explore the kind of similar content as I have in the website.
Cool, sounds good. So we do have a question from the audience. Alid Sage asks, how does the Python NLTK compare to the Amazon Comprehend service for your use case?
I haven't actually used the Comprehend. Sorry about that. If I'm right, it's something quite similar to Alexa. So I did have used Alexa or Google's Dialogflow for some other projects. So I can't really compare this with Comprehend. Sorry.
No worries. So the other thing I was wondering about your solution there, the use of ECS tasks to start a processing job in the background as people search for things that haven't yet been, I guess, fetched and processed. Does that scale up? Like if you suddenly get loads and loads of users on the website, does the ECS platform fire as many tasks as there are people? And what are the sort of limits and the implications on cost, I suppose?
So that's again a very good question. So in theory, it can scale up because Fargate is as introduced this virtual container. You can you don't really have a bottleneck in terms of your infrastructure or physical resource underneath. But AWS do apply a kind of sort of limit, and also you can have a setting in your AWS project as well. How many concurrent jobs you can run on this Fargate container, Fargate cluster at a time. So yes, as a matter of fact, at the moment, if there are people simultaneously searching for names that have not been included by the website, it will not be able to accommodate all of the searches at the same time. Yeah, but the idea of the currently the website has like 10,000 people. I guess this case is based on the current usage, it's quite rare. Yeah.
Yeah, got you. Cool, good stuff. Looking forward to seeing where you take that next. Thanks for joining us. You're going to join us later for a bit more of a discussion with some of with our other speaker and with Bernard. So do stick around, and we'll talk to you later on. Thanks very much.
No worries. Thank you.